And then we'll use another instruction. We'll put something like, let's see, 2, 3, 4, 5 into AX. Now, when it's AX, we have to change the length to W to be consistent. And then we'll move B, move byte. And we have 6, 7 into A. Oh, let's deal with AX first. And then we have move byte 8, 9 again. Okay, well, got just enough digits to do it. So 8, 9, we'll put it into AL. Okay, so those are the instructions, and we want to find out what it's going to do in this particular case. PBX. So that's my entire program. Now my objective is to find out, by the time we get to the move L, $1 instruction, what would be the content of EAX. Now, one quick way to find out what would be the content of EAX is to run the program, right? I mean, let the debugger tell me. But that kind of defeats the whole purpose of this program, because I want you and me to figure this out line by line, so that we know what it's supposed to do. We run it in the debugger just to verify our understanding is correct. Okay, does everybody understand how we should treat demonstration programs in this class? And I'll do tons of demo programs in this class. All right, so let's go ahead and do this step by step and figure out what will be in EAX in this case. All right, so what we'll do is we're going to do the same thing as in the spreadsheet. Okay, so we'll spell out the 4 chunks in in that portion of the CPU. So we have bits 24 to 31. We have bits 16 to 23, 16 to 23, and then we have bits 8 to 15, and then we have bits 0 to 7. After the first instruction, what should we be seeing? What would be the most significant nibble? AB, exactly. So AB is the most significant byte. CD, EF, and then we have 0, 1 here. So that will be the result of the first instruction. The second instruction does not affect the most significant bytes at all. It only affects the least significant 16-bit. So what do you think will be here in bit 8 to 15? 2, 3, and then we have 4, 5. What about this instruction here? Which column are we affecting? 8 to 15. So that will change. That will be changed to 6, 7. What happened to the other 2 columns? What happened to bit 24 to 31, 16 to 23? Absolutely nothing, right? They're unchanged, completely unchanged. Okay, and the last instruction only changes the least significant byte to 8, 9. So after all of these instructions, if I have to make a conclusion, then we should end up with AB, CD, oops, 6, 7,
Yeah, or 6, 7,
and 8, 9. Okay. Now, this program won't compile because this is not syntactically acceptable. So I have to basically mark these as comments. I use the pound sign to indicate comments. So everything from the pound sign all the way to the end of line will be ignored by the assembler. Same convention as in Perl, Bash scripts, and all of the other Unix-like, earlier Unix-like programming languages. All right, so now we can actually run the program and see whether our comments actually reflect the result of those instructions. So we'll go ahead and assemble. Link and debug. List the program, find out where to put the breakpoint, line 5, and then we run the program. Now we're on line 5, just to make sure that EAX has, doesn't have this value to begin with. We just do an IR, which stands for info register, and it has 0 in it, okay, which is which means it's just initialized to 0. I single step line 5, and then we look at IREAX again. It has A, B, C, D, E, F, 0, 1, which is exactly the way we predicted A, B, C, D, E, F, 0, 1, which is fine. Now we are about to execute line 6. Line 6 is going to do a move word to affect only the least significant 16-bit. So we single step, we look at the entire register EAX again, and we can see it is ABCD because that part does not get changed, but the least significant portion becomes 2, 3, 4, 5, and this is also predicted as 2, 3, 4, 5. Now we are going to put a 6, 7 where 2, 3 used to be. So we single step line 7 at this point, do another IREAX, and you can see what used to be 2, 3 is now changed to 6, 7. And now we can single step one last time to affect the least significant 8-bit of EAX. And then we take a look at register EAX again, and we can see that it is ABCD 6, 7, 8, 9, and that's exactly the way we predicted it. Are we doing okay so far with this code? Okay, so the endianness of how we organize memory is actually can be important. Okay, now with this example, it's not important because we only use immediate operand, okay, to directly affect a certain part of the 32-bit register. But if you try to load from memory into a register, then it becomes important because the least significant byte is the one that is at the lowest address. So that part becomes important again when we start to talk about memory operand. And we haven't really started on memory operand at this point. So getting back to the spreadsheet here, is it clear what this means? Okay? So this is kind of like a graphical representation, and then the sample program really illustrates what it means to be, to have access to AH, AL, AX, and EAX. Yep.
Sir, any way to access the most significant bits of EAX?
Not by itself. It does not have a name to refer to just that portion of the register. Okay, that's a good question. Now, we're running out of time. We got about 1 minute and 10 seconds. So what I'll do is I'll point out where in the notes you really should be reading and probably have it finished by the time we start the class on Thursday. I would finish up section 5. So section 5, I would actually go through all of it because most of these are related. So once you get to one memory operand, the other ones will be kind of pretty simple too. So I would go through the entire section 5 here. And for those of you who are overachieving and really want to get something to do, start on this one. Start on adding in topic 3. Even though we talked about adding a little bit earlier, this is a little bit different. And for those of you who really want a challenge, go to subtracting because subtraction is actually more fun, especially with comparing. All right. So we still got 10 seconds left. You're not going to get a refund for those 10 seconds. I'll see you guys at the lab. Yep.
So
no refund.
At the end of each program, you put like 0.